Hi folks, we'll take a look at a couple of examples of finding derivatives involving logarithmic functions. Okay, so we'll start with this one here on the left. So here I notice I've got the natural logarithm of some expression. So first thing would be to think of using the chain rule. But what I'd like to remind you of here is that we have some nice properties with logarithms. So I have the logarithm of an expression squared. So I can actually simplify this function quite a bit by using the ski-slope rule. Okay, so the first thing I'm going to do is I'm going to take this 2 down in front of the logarithm, so I can rewrite this as 2 times ln of x squared plus 3x minus 4. Okay, and now I end up with having to take the derivative of a much simpler function because this 2 now becomes a constant. So could you have solved this problem without doing this? Yes, it would have just meant using the chain rule a couple of times, but try to keep in mind that when you're dealing with logarithms and your input has a power, that you can use that ski-slope rule. Okay, so now I'll go ahead and take the derivative here. So this 2 is just a constant, so this is just 2 times the derivative of this logarithmic function, but of course this is not natural log of x, it's natural log of a more complex expression, so that's what's going to become my u. Okay, so here the derivative of ln u is 1 over u. So this is going to be 1 over x squared plus 3x minus 4. Okay, and then I multiply that by the derivative of u with respect to x, and that's a nice easy derivative, so that's just 2x plus 3. Okay, so here 2x plus 3, I suppose I could try to factor this thing in the denominator, which I could. Okay, but I don't think it'll cancel out with anything in the numerator, but we'll do it just in case, just to show how we could then use what we have to, determine things about the derivative. Okay, which often involves finding the zeros of numerator and denominator. So here we've got 2 times 2x plus 3 in the numerator, and in the denominator we can write this as x plus 4 times x minus 1. Okay, so there you have it. Again, just a reminder, this little trick that the ski-slope rule might come in handy to simplify the derivative, and then that allows us to only use the chain rule one time. Okay, let's move on to this other one here. Now notice here I can't use the ski-slope rule because it's not the input x which is being squared. It's the whole expression ln x which is being squared. So just keep in mind, here I can't apply the ski-slope rule. It doesn't apply. Okay, so the first thing I notice here is that I've got a quotient of 2 functions, so I'll have to use the quotient rule, and then looks like in finding the derivative of the numerator I'll have to use the chain rule. Okay, so let's go ahead and do that. Okay, y prime, and in fact the first thing we have to do is determine the derivative of this numerator function. Okay, so here I see that I have ln x squared. Okay, so I have the derivative of something squared, so that's going to be my u. So derivative of u squared is 2u, so 2 times ln x, and now I have to take the derivative of this u, and the derivative of ln x is 1 over x. Okay, so there's the derivative of the numerator. Okay, now I have to multiply that by the denominator function, okay, times x. So actually it looks like it'll be quite nice. So then minus, okay, the numerator function, which is ln x squared, multiplied by the derivative of the denominator, which is just 1. Okay, and all that over the denominator squared, x squared. Okay, so let's go ahead and simplify this here. So here I've got the x in the denominator reduces with the x in the numerator. Okay, and when I look at what I have left over, well, again, I've got a common factor. I've got an ln x in both of these terms. Okay, so let's factor that out, ln x, and then we're left with, well, it looks like just 2 on the left, and on the right we're left with that other ln x. So 2 minus ln x, and then all over x squared. Okay, and that's in a nice form. If we had to do anything with it, like determine the zeros of the derivative, you can do that quite easily in the numerator. Okay, so that's it for these 2 functions. So again, just to recap the second one, obviously we have to use the quotient rule. Okay, and then in there, when you're simplifying, again, always look for those common factors.